Okay, welcome back, ladies and gentlemen. Now we are going to start our second session, decarbonization. So now I would like to invite on stage our next speaker, Mr. Kuniadi Wandy Huang. He is the researcher at IMarEST, Center of Excellence at NTU. His topic is about decarbonization, challenges and opportunities for the maritime industry. Please welcome.
Okay, good morning, everyone. My name is Wandy, and I come from Maritime Energy and Sustainable Development, or MEST Center of Excellence from NTU. So today, we would like to have a presentation on the decarbonization challenge and opportunities to the maritime industry. So before I'm going to talk more about the decarbonization, I would like just to introduce. Sorry. So I just want to introduce you briefly what is our center is doing. So MEST is a leading global. Our vision is to be a leading global translational research center in maritime energy and sustainable development. So our aim is to be the bridging between academic and industry to conduct research up to commercialization level, of course, with the support of the government and also with the companies locally or internationally. So this is some part of our research focus. We conducted mainly research on green ports and shipping, where it can be divided into three research focus: energy management, emission management, and also a sustainable maritime operation. Our research focus is also in line with SMI Roadmap 2030, which is on the sustainable maritime environment and energy. So sorry about this. So this is some of our showcase. We conduct a lot of research related to alternative source of energy, such as international shipping, multi-purpose port, container port, and also harbor craft. This is some of our R&D projects. We do research on the alternative fuels, multi-purpose port, prime movers. We also conduct a lot of onboard testing, especially the energy and emission performance management system, study on methanol, ammonia, hydrogen, and also electrifications. So we also work actually together with industry to our external projects. So we develop a lot of systems related to emission control, such as simultaneous removal for SOx and NOx for ships, selective catalytic reduction for NOx, and most of our recent project is also an application of carbon capture technology reduction for a reduction of GHG emissions for ships. So this is some of our activities. So you are welcome to talk to us, and maybe in the future, if you are interested, we can work together, conduct some research, mainly towards green shipping, toward decarbonization. Okay, so now let's. This is some of our reports. You're welcome to visit our website. So we have published a lot of public reports, especially on alternative fuels, electrification, methanol. You can download it for free to our website. So we are welcome to read some of our reports about this. Okay. So now let's talk about the decarbonizations. So we know shipping play an important role for the global industry. So shipping conduct trade for more than 80% of the trade volumes. However, in order to do this, ships need to burn fuel. Then, in fact, actually, it's produced CO2 emissions. In 2019 alone, it actually produced more than 900 million tons of CO2, where generally it's dominated by two types of ships: dry bulk, tankers, and containers. So IMO aimed to reduce this greenhouse gas emission through different parts of measures, starting from short-term measures, mid-term measure, and long-term measures. A recent study from IMO fourth GSC study in 2020 shows quite a significant improvement through our 2008 emissions. So starting the emission of 2018 is almost similar to 2008, which is a great improvement. But the projections still show that the emission will increase from 90 to 150% in 2050, which is still a big gap towards IMO targets in 2050s. So how actually we can go for decarbonizations. So in general, there are three major categories for ship decarbonizations. First is technical and operational measures, alternative fuels, and lastly, but not least, is carbon capture, storage, and utilization, which I will discuss one by one in general in the next few slides. So for T&O measures, is actually the aim is actually to make the ships operating more efficient. So this parameter usually using an indicator such as EDR and EXI, which I think everyone knows. EDI is for the new ships, and the upcoming regulation EXI will be in 2023. So also I am also introduced carbon intensity indicator, or CII, where actually the aim is actually for ships continue improving their emissions and including checks annually. So according to recent study by NAPA, EXI is implemented to reduce carbon intensity by around 4.6% for both carrier, while CII aims to reduce the emissions up to 11% by 2026. Emission here means the carbon intensity. However, the T&O measure itself is not sufficient for to meet the targets. So one of the solutions is we need to work together with T&O measures and find other alternatives solutions such as alternative fuel or maybe CCUS. So when we talk about alternative fuels, it can be divided into four major categories. So first, as we know, is conventional fuels. This is under categories such as MGO, NGO, PLSFO, etc. The second type of fuel is alternative fuels containing less carbon. This can be LNG, methanol, and its derivatives. The third one is the alternative fuels containing biogenic carbon. Biogenic means it's come from biological sources such as plant, tree, and soil, etc. The fuel under this category can be bio-LNG, biomethanol, HVO, and others. And the last one is the alternative fuels containing no carbons. Fuel under this category can be electricity, hydrogen, and ammonia. Okay, so there are so many fuels out there. So actually, what is the consideration that we need to decide? So this figure actually shows the performance of different types of fuels based on three categories. First is the GHG reduction potential. Second is the cost per energy unit, and third is the TRL level. So as you can see here is when we talk about the GHG emission here, this figure actually shows the emission based on well to wake. This means it's also considered the emission from the fuel production until it is burned on board ships. So why this is important is because fuel can be divided into different categories such as gray fuel, blue fuels, and green fuels. It's important, for example, when we talk about ammonia. When we talk about ammonia and when we talk about gray ammonia, in fact, actually, it produces emission through their process because their main source is from the natural gas. So in fact, as an overall GHG reduction, it might not have really GHG reduction saving compared to HFO. But when we produce ammonia in a green way or green ammonia, the GHG reduction potential actually can reach up to 75%. So it is very important for us to see how the fuel is produced because we want to see the overall GHG reduction potential. The second one is the cost. Of course, typically at the moment, all fuel that produced through a green way or green pathway generally is more expensive than HFO. Of course, this might not be applicable for the future. Once this type of fuels gain more upticks, the cost might drop further in the future. The third one is the TRL level. All this technology of green really shows promising results. GHG reduction can reach 70% or maybe even 100% or more. But the TRL level, for example, for green ammonia is only between 3 to 5. It means that although the technology promising, maybe more time is needed before actually we can use this type of fuel for ships. The next is the energy density of the fuel. So why energy density is important? Because when we would like to have a higher energy density per weight of volume, because with the same amount of fuel, it can produce more energy. So this is important because the energy density of the fuel partly determines how applicable the fuel is for certain ships and ships operations. Okay, so the third solutions is carbon capture, utilization, and storage, or CCUS for ships. CCUS means ships can continue burning conventional marine fuels such as MGO or HFO, but they will install some kind of exhaust gas cleaning system after the internal combustion engine, where their CO2 will be captured, and either it is to be utilized further or to be stored on board. Then it will be transported to land for further storage and utilizations. CO2 generally can be stored either deep below ocean floor or saline aquifers, or CO2 actually have the potential also to be utilized further, either to be converted to be another fuel such as methane or methanol, chemicals, building materials, EUR, food and beverage, and others. So in general, of course, we talk about the CCS, but in fact, actually, the CO2 capture itself have a different methods. There are three main general methods to capture CO2, which is pre-combustion, oxy-fuel, or post-combustion. The definition is quite straightforward. Pre-combustion means the CO2 is captured before combustions. Oxy-fuels mean you replace the air with concentrated oxygen. Post-combustion capture means you don't make any significant modification to fuels and engine system. You just install an exhaust gas cleaning system to capture the CO2 after the emissions. So the question is, which one of this technology is suitable for ships? Actually, it very depends on a few factors. For example, for pre-combustion captures, fossil fuel is burned. Then in the end, actually the fuel produces hydrogen. Then the hydrogen will be burned in the engines. So there will be a significant modification to the engine and fuel systems, and there will be a significant investment. So pre-combustion is not possible for existing ships, but it can be considered for new ships. For oxy-fuels combustion, it's possible for both existing and new ships. However, the technology at the moment is not yet mature. The PR level is still not in line yet. It's still in development. It also requires significant modification because you need to install a unit to separate the oxygen from the air. For post-combustion capture, it has more flexibility. It's possible for existing and new ships. It has a high investment cost, but it's typically lower than both pre-combustion and oxy-fuel combustion. The issue of the post-combustion is the process is energy intensive. The CO2 come out in a diluted concentration, and it also has impurities which might affect the system. So when we dig more, post-combustion capture, although there are a lot of technologies out there. In general, it can be divided into four, such as absorption process, adsorption, membrane, and others. So actually how we can determine or how shipowner can decide which technology actually have the potential to be used for ships. Right? So this figure shows the technology readiness level of different carbon capture technologies. So as you can see here, a lot of technologies, including not only post-combustion capture, but also pre-combustion capture and oxy-fuels are below TRL7. Because the challenge here is actually for TRL3 is you need require a significant R&D to pass through the TRL7, you need significant commercial investment or industry interest. Between all these technologies, the most mature technology is actually called amine-based solvent, which is the typical chemical use is MBA or monoethanol amine. In fact, this technology is considered most mature technology for land-based application. It has been installed in many of the power plants and is proven to work really well. But this TRL level, it is still not exist for land-based. So the TRL level for ship application is expected to be lower. Why? So in the next slide, we a case study try to compare what is the impact of using directly the amine-based application for land-based ships. So here on the left side, you can see the diagram of the estimated cost between the CCS for land-based application and shipboard application. In the first three, the CCS is installed for either cement plant, steel, or power plants. The estimated cost for CCS is around 40 to 50 USD per ton CO2. But when the same system is installed with ships, the cost is significantly higher, which is $82 USD per ton CO2 only for 70% capture. And if you want to increase the capture to 90%, the cost increase significantly. There are two main reasons of this. First is the capacity. Normally, the CO2 capture on power plant have much more volumes. It means that it can lower the capex in general. The second one is the concentration of the CO2. For power plant, typically the concentration of the CO2 can be more than 10%, but the concentration of the CO2 from ships is usually much lower than 10%, maybe between 4 to 6%. So in addition, the table on the right also shows that this process for MEA, if you use as it is an energy intensive process, and it's also have huge footprint. You need to consider the absorber and dissolvent resorption unit, the CO2 storage, and also for amine tank. So the takeaway from this slide is actually, although MEA is a proven technology for land-based, actually it might not be directly applicable for ships, and actually you need to some further research and development to modify the existing system for ships. In fact, some industry, the well-known players such as Mitsubishi and MRI with Alfa Laval and also Samsung Heavy Industries are also exploring to install and develop CCS on board. And from what I know, they are also using the amine system because based on the PRL level, amine is already proven, while other technologies maybe it's a promising, but at the moment the PRL level is still low, and it will be a huge gap need to overcome if they want to consider other technologies than amine. So next, so in all these previous slides I introduced, there are so many solutions of alternative fuels. Alternative fuels also, there are 4 types of fuel that you need to choose. For CCUS, you also need to decide what technology that you need to use. So what is the challenge or tool for the ship decarbonization of the emissions? So in my views, of course, there is no one solution fit for all, but I believe that for all these considerations, the ship owners or people or players in the maritime industry will have these 4 concepts in order for them to select the solution for the ships. Of course, it's mainly technical, economic, environment, and safety aspects. For technical perspective, you need to consider what type of ships that you have. What is the available resource you have? Like different type of ship may have a different available space, different available electricity and power. What's your engine? Whether this is a new ship. So when you talk for the new ships, maybe you can consider more into the alternative fuels because you have much more flexibility in designing the new ships. But for existing ships, you have a lot of limitation resources. Then you might need to consider whether you can consider need to use installed CCUS or you can use alternative fuels without many significant modification to the engines. Of course, the complexity of the system is important, and the supply chain infrastructure, especially for those new fuels such as ammonia and hydrogens. Economics, of course, the solution selected must make sense economically in terms of capex, OPEX, ROI, and carbon tax. Environment, we don't want at the expense of reducing CO2 and introduce additional or unwanted byproducts to the air. For example, methane leaks, which is, yes, in our game, we are trying how to improve or minimize these methane leaks. For the CCUS, the concern is who will receive this CO2. What is the infrastructure will be on ports that ready to accept this CO2, how to storage it, and how to utilize it. So in the end, this slide shows what is the forecasted pathway for ships decarbonizations. As I mentioned, there is no solution fit for all, and it's very different. A lot of organizations do their own projections based on certain assumptions. Some predict maybe the LNG will become a dominant fuels in the market. Some estimated hydrogen and ammonia, and I believe that none of this result is wrong because at the moment the situation is very dynamic. In the end, I believe that the type of fuels or the technologies that come on top will be depend on how fast the technology goes into the commercialization, and also whether the infrastructure can be really fast and can be readily available for ships deployment. So in the end, at the moment, the use of the conventional fuels, I believe it's still predicted still to be around, at least until the uptake of all these alternative fuels are ready. So the path toward ships decarbonization could be shared either by conventional fuel plus CCUS or alternative fuels, or combination between alternative fuel CCUS, and eventually at the end of 2050, maybe it will go towards no carbon fuel. So this is the end of my presentation. Thank you so much.
Thank you very much, Mr. Kuniadi Wandy Huang, for delivering the speech. So now I would like to invite on stage our next speaker, Mr. Sobhith from Global Newbuild Support Manager from Lloyd Register, to deliver his speech, Application of Methanol as a Fuel for Container Ships. Please welcome.
Good morning, everyone. First off, thank you very much, organizing committee for this opportunity. My name is Sobhith. I'm working with Lloyd Register based out of Singapore office. And in my role, mainly I'm supporting ship owners and charterers, design houses and all those, mainly in terms of ship new build projects, projects related to alternative fuels, decarbonization and all of that. So I've been working with LR for almost 16 years, and previously heading the engineering team here in Singapore for South Asia region. And previously I've also worked in our offices in Korea, Busan, mainly looking after LNG carriers, Shell Prelude FLNG project, and previously also in office in UK, mainly on LNG as fuel related projects. So today I would like to share with you on the application of methanol as a fuel for container ships. So incidentally, when the same IMarEST RENA session last year, I had an opportunity to present on ammonia as fuel. So when I was discussing this with one of my colleagues, and he was asking me, so why are you confusing people with this mix? Like last year is talking about ammonia, and this year is about methanol. Why is it that you guys do not have like a one fuel which the industry can focus on? So luckily for us in this audience today, we have heard enough from our speakers, earlier speakers, in terms of the need for perhaps a mixed fuel mix going forward, complying with all those requirements that we are supposed to be complying with in the next couple of years. So about Lloyd's Register, again, we are basically a classification society. We fundamentally focus on ships, offshore assets, and all those. And in terms of the safe operation on the sea. So again, this graph is just to remind us all in terms of why we're discussing about this at the first place, all the greenhouse gas reduction pathways from IMO. So we are expecting at least to get a reduction of 50% of the CO2 equivalent emissions as what we had back in 2008. And that we would like to achieve by 2050 at least. So as we have seen or heard from earlier presentations, so we might be looking definitely at a mix of fuels, and a graph from Clarkson's that you see on the right is basically telling us how the new build fleet development might look like going forward to 2050. So the oil fuel fleet is actually the graph or the curve on top, and it's expected that we will see a decline starting from this year onwards, going forward to 2050. And by 2050, we will be seeing a mix of fuels. So like, for instance, zero carbon fuels could be, for instance, ammonia, methanol, and all those, close to a 34% of the mix. And LNG, maybe around 34% of the mix, with still some other fuels and oil-based fuels still in the mix. So when we look at, let's say, the adoption of alternative fuels, there are maybe some brief factors which we need to consider. So essentially, we want to see that the regulatory development is also paving some way. So essentially for the pathways or the strategy, IMO has done that part. And of course, we will see more and more regulations coming up. For instance, we have seen EEDI come up, EEXI coming up, emission-related other requirements like, for instance, CII coming up. We might also see more of these coming in the next couple of years. For let's say EEXI phase 2 perhaps, or a EEDI phase 4 perhaps. So essentially all of this will provide initial or a sufficient buffer or sufficient pressure to the industry to adopt all those alternative fuels. And essentially the technology also have to be ready. So of course, in terms of the engines, the fuel preparation systems, the fuel containment systems, all of that, we need to have the technology readily available and with sufficient in-service experience so that owners, operators, and all those will have sufficient confidence to invest in this and operate. And all the fuels that we discuss on, they also need to be available in a suitable locations to cater to the fuels of the vessel's operational needs. So essentially, going back to the energy density topic that we discussed in earlier presentations, finally, the energy cost of using these fuels will also have to be looked into. So looking at the energy density, we are seeing considerably lower energy density as opposed to the fossil-based fuels for zero carbon fuels. So that would mean that we will have to consume more and also pay more to transport these cargo on vessels using these particular fuels. So some form of carbon levy or some form of an incentive for owners and operators to invest and operate these vessels will have to be in place. So methanol, as we discussed, forms one of the options. So essentially just this slide is to give a very brief overview in terms of what methanol is. So methanol, it's a alcohol-based compound, and of course, currently it's being produced extensively from fossil-based sources, such as natural gas or coal. And in the industry, there is sufficient experience in terms of transporting it on board chemical tankers, methanol carriers. And in Singapore, previously, we used to have a lot of offshore supply ships carrying methanol as a cargo for offshore applications. So there is sufficient in-service experience, and in terms of storing it on board, it can be stored, let's say, in liquid, as a liquid in ambient conditions, as opposed to some of the other fuels that we're looking at. And in terms of, if at all there is a spill, it is still considered much more safer than other fuels because it's still biodegradable. And it also offers some level of reduction in terms of the emissions itself. But there are also some challenges. So for instance, it is a corrosive liquid. It also poses some toxicity risk to people who are exposed to this, or for instance, the shipboard crew who will have to operate methanol fueled machinery or do bunkering of this. And then to cater that, we will have to install additional safety systems, which are much more complex than what we now have on board. So that said, let's also take a brief look in terms of how the availability of methanol and how maybe the future availability will be will also be influenced by some of the regulations that are coming. So currently, more than 90 production plants with close to 100 million tons per annum produced. So as you can see, the mix is now currently almost 65% coming from natural gas. But going forward, that may not be sufficient because all the life cycle emissions related regulations or requirements are coming into play. So that might have an impact in terms of what this particular fuel and how it's going to be produced. So in terms of IMO, the draft guidelines for life cycle emissions analysis for these fuels are being developed. So these will have to be complied when we consider these sort of fuels or zero carbon fuels or even fossil-based fuels when we use on board. So with those regulations, this is how the fuel mix might change. So in terms of methanol's availability in a green or let's say a blue based, like the color code of the fuel based on how it is actually produced. So IRENA suggests that close to around 250 million tons per annum could be available by let's say 2050, and that's in synthetic methanol, and close to 135 million tons per annum in terms of bio methanol sources. So essentially what it says is if the industry is investing in methanol fuel ships, by the time these vessels are operating, these fuel in sufficient quantities will also be available. And these are just some of the news clippings from recent articles. So you can see IMarEST is actually pioneered this and has catered a lot of interest in the market, just not just for using this as a fuel, but also to produce, for producers to produce methanol in sort of greener ways. And even in Singapore, there are plans to actually do a feasibility study to say if it could be feasible to set up a plant, e-methanol plant based out of Singapore. So again, all of this is going to cost consumers like us more money, because also there is a clipping from Maersk management in terms of they expecting at least double-digit premiums in terms of the freight rates as a result of using these particular fuels on board. So of course, someone has to pay for this eventually going forward. So in terms of statistics, we are looking at close to around 15 ships, container ships, and also tankers currently in operation. And around 28 ships are on order. And it's forecasted that by 2030, we could see in water close to around 80 vessels. And currently, mostly methanol tankers and container ships, but interest is also actually building up on all the other different ship types. And as we discuss this with ship owners, there is also increasing interest in their perspective to see how maybe perhaps a retrofit could be considered going forward. So what about the regulations? Where does it actually stand now? So in terms of as carrying this as a cargo, the regulations are all very well developed. So we carry that under the MARPOL Annex 2 requirements and also the requirements from the IBC code. In terms of containerized cargo, the IMDG code also provides sufficient regulatory requirements. And in terms of fuel, IMO has released the draft guidelines, which with very prescriptive detailed requirements for the application of methanol in terms of its storage on board, in terms of processing it on board, the safety systems and all of that. Lloyd Register, we have also been working on this for many years, and we have our own rules detailing all those requirements to ensure the safe application on board. In terms of the standards, bunkering, so we have also developed a bunkering, methanol bunkering reference, technical reference document, which has been used extensively in the industry now for handling methanol bunkering operations. And in terms of the standards, ISO is also currently developing a marine methanol fuel standard. So that's work in progress. So regulations, as we can see, is more or less fully developed. And in terms of the technology, so we can see methanol fueled engines are in operation for more than 7 years. So methanol tankers, chemical tankers are using these engines from MAN. And we also expect engines from WinGD using methanol to be released close to Q2 of 2024. And in terms of auxiliary engines, there are also developments in place. Wärtsilä has developed the 32 series engines, which could use methanol. Hyundai Himson is actually developing engines which could also use methanol as a fuel. And we have also worked on conversion of these smaller engines, essentially for the first conversion project that we did in Sweden for Stena Germanica project. That was a conversion of a diesel fuel engine to use methanol as a fuel. So all of that is actually possible, and technology to a certain extent is readily available. So we wanted to establish or investigate this a bit more further. And as part of that study, we evaluated a fleet of container ships operating in Asia. So a green corridor study was undertaken, essentially looking at what sort of fuel pathways these vessels could actually look into. So we examined methanol as an option, ammonia as an option, and also hydrogen as an option. So how could we transition now from what it is now, let's say mostly LSFO or MGO, to all those renewable fuels in future? And as part of this study, we also wanted to look in specifically in terms of what could it take to use methanol as a fuel on a feeder vessel of this particular profile. So we looked at this particular case vessel, so close to a 3,000 TEU container ship, and essentially looking at how and what it's actually required essentially to use methanol as a fuel for this particular ship. And we looked at carrying capacity for close to 3,500 cubic and looking at an endurance of 10,000 nautical miles at a speed of 18.5. So estimated that close to 20 to 25,000 tons per year of methanol will be required. So that's just looking at engine operating, let's say at 50% load and roughly for around 270 days of operation. So just very high level estimates of this. So this diagram is just to give an overview in terms of what could be required. So essentially we need to have provision for storage. So storage tanks, provision for bunkering, and some form of processing it. So it's high pressure, some pumps, heat exchanger units, filter units. And this was considering the main engine. So there will be a fuel valve train controlling the fuel supply to the engines, and also perhaps in some forms controlling the water injection to the fuel if you're adopting that as a means for NOx emissions reduction. So then there will be the main engine, the consumer itself, and some form of small drain tank and service tanks and all of that. So this could definitely differ from engine maker to engine maker, and depending on the type of engine that we are actually looking at. So just to give an overview, these would be some of the systems that needs to be put on board, let's say if you're considering a vessel. So essentially, we also wanted to look at it from a risk-based perspective. Of course, the draft guidelines are there. There is also the rule requirements, but we also want to ensure that the risk the risk due to these additional systems on board, the additional containment of methanol on board, processing it on board, are also addressed. So from a Lloyd's Register's perspective, we normally look at it from a risk-based certification method. So essentially looking at what specific risk could come up as a result of adding these components on board, storing this methanol on board. And then we will run this through hazard workshops and a hazard workshops essentially to understand the specific hazards and what specific mitigative or preventive measures are put in place to address these particular hazards. And just to give maybe an illustration of how we have done that on the same system that we looked at the earlier slide, I'll share some brief. So this is essentially looking at the one particular part of the system that we saw earlier. So the bunkering operation, and also going into the storage tanks. So essentially, when we put this through a risk-based sort of certification method, we are looking at this particular node, and we are trying to find out what specific hazards could be as a result of this bunkering operation. So it could be methanol leakage, and also as a result of that leakage, personnel who are perhaps exposed to this could be exposed to toxicity-related risks. There could be some fire considerations because methanol again is a low flash point fuel, and there could also be contamination of the fuel, and essentially risk due to the specific location of the bunkering station. If it's located too close to the accommodation area, or is it located maybe near to a location where we have, let's say, the lifeboat, or if it's emergency escape route. So once we know these hazards, it's essentially next step will be to identify or put in place some of the preventive or mitigative measures. So once we know these risks, we are looking at preventive or mitigative measures such as, let's say, showers or eye wash or essential PPE for the packs, emergency shutdown systems, remote monitoring of, let's say, the bunkering operations. So essentially, some of these are covered under the prescriptive requirements given under the interim guidelines from IMO. And we could then look into additional systems like, for instance, specific firefighting systems for this particular location, provision for vapor detection, and some form of action initiated as a result of the methanol being released. So in the same way, we could run that for this methanol onboard storage facility. So what could happen if there is this particular methanol storage tank or the service tank, if it is compromised, if there is a leakage from the storage facilities. So we could look specifically into the hazards and then essentially look into the preventive or mitigative measures that could be put in place. So if there is, let's say, a structural integrity issue, or there is a collision, of course, we are looking at a protective location for this particular tank, provision for essentially coffer dam to protect the tank contents from any form of heat ingress from, let's say, if it is located adjacent to a machinery space. So those kind of provisions can then be put in place once we know these are some of the hazards. So essentially, that's how we sort of evaluated this. We looked into a particular design. We looked into a container ship. What could it take to operate a vessel using methanol as a fuel for a specific container ship? So we looked at some of the systems that has to be put in place, and then what sort of measures or safety measures has to be put in place to address some of the risks associated with its sort of application. So in summary, we know that the technology is available. So we have seen in terms of the engines are sufficiently developed sufficient in-service experience, in terms of the process systems, in terms of tank containment systems. It can be contained on integral tanks with sufficient amount of coating. So all of that is in place. And in terms of regulations, classification requirements, statutory requirements, and all those have developed sufficiently. And in terms of in-service experience, a number of new build vessels are in order. A number of vessels are also operating. So experience in that front is also there. So in terms of the life cycle emissions, or in terms of how the methanol production could cope with the upcoming life cycle emission related requirements, so that's a specific issue. So that will be addressed through the regulations once it comes into place, and also through extensive investment by again parties producing methanol. So that's something that has to come up. And in terms of the safety systems on board, once we run this through the risk assessment sessions, and once we run this through the risk-based design methodology, all of those risks associated with its use could be safely managed. And with that, I would like to conclude. Again, thank you very much for your time, and I will be happy to take any questions during the panel session. Thank you.
Thank you very much, Mr. Sobhith, for your delivering the speech. Now I'd like to invite on stage our next speaker, Dr. Imran Ibrahim, Principal Consultant, Head and R&D from DNV Maritime Advisory. His speech is Alternative Ship Fuels, Status and Outlook. Please welcome Dr. Imran Ibrahim.
So good morning, everyone. Thanks again for the opportunity to speak. Where we are right now, I think we've had the first presentation from MESD, dealing a more generic perspective, alternative fuels. Then we went to something more specific on methanol, and now we're going to something again more generic again. So I'll give you a perspective of what is the current status and outlook of the alternative ship fuels. This is the overview of my presentation. I'll give you introduction, regulatory update, and move on to alternative fuels, current status, and also market activities. And I will round up with how DNV supports the owners, banks, and insurance in this service. Yeah. So there's no doubt of the importance of the topic that we are discussing today. The question is of the alternative fuel selection is one of which we get often these days. And there are very good reasons for this. So the short answer is, as we have heard, there's no silver bullet. Don't see a solution that fits one size fits all. And we need to consider recent developments and then figure out the most appropriate solutions here. The picture today is that not only IMO is driving this change when it comes to environmental matters. Of course, IMO is a very important player. I would say the most important player. But in addition to that, we have other drivers, such as the European Union, which is moving quite fast in this space. We have the banks and the finances, who with products like climate bonds. We have the Poseidon Principles scheme for assessing the environmental performance of the vessels. And we have stakeholders like the Sea Cargo Charter agreement coming from the charterers. So in addition to that, individual cargo owners having their own requirements for environmental performance. So it is pretty clear that the pressure is coming from all sides. Yeah. And it's going to be increasing as we move forward. We are quite familiar with what's coming from IMO right now. So this is the CII, or the Carbon Intensity Index, and the accompanying SIMP, or the Energy Efficient Management Plan. So this is an accompanying plan together with, connected with the carbon intensity indicator of the vessel. It has to be submitted on an annual basis, depending on whether the vessel is going to be on CII scale. Energy Efficiency Management Plan has to be updated The annual process is to make sure that the vessels are improving their performance. So the targets of the CII will be decided up till 2026. At this stage, there's no agreement of the targets period for up to 2013. It will remain to be decided only in 2025. And we can only, again, expect that the targets will be more stringent, specifically for shipping. Sorry, last summer as well, EU published the EU Fit 55 proposal, comprising of 4 measures that are relevant to shipping. So I'll be focusing on the first 2 here, which is the EU Emission Trading System, the ETS, as well as the Fuel EU Maritime in the subsequent slides. The EU ETS has been in place for several years. This is a carbon pricing scheme in Europe, and next year shipping will be a part of it. There's a phase-in period from 2023, which includes 20% of the emissions in the scope, increasing exponentially to 100% in 2026. There is also actually another proposal now, which may hasten this increase. But the key takeaway here is that, again, there will be a pricing for carbon. So as you can see from the graph, cost per ton of CO2 has been increasing. It was stagnant initially and then increased exponentially. We are now at approximately $270 per ton of fuel. So this will be a very significant cost. The scope. Well, next year, all ships calling European ports will be subjected to cover 100% of intra-European voyages, with 50% of inbound and of the outbound legs. So this is going to be based from your EU MRV system. What you can do to reduce exposure is that the fuel is that to use low carbon content, for example, LNG, will reduce the cost by about 20%, and or go with the option of advanced biofuels, for instance. The Fuel EU Maritime. So this is another important regulation. This is going to be, again, the first for maritime, because it takes into account the life cycle of the fuels, including regulations. So now it doesn't matter how efficient your vessel is. What is important here is that even the most efficient vessels will have to use a low carbon content in the fuels. So come 2025, when this comes in force, the requirement is to have about 2% reduction in carbon intensity, and then it goes down to 6%. So the graph here basically denotes the proposed reduction rates, and the example default values from the different fuel types. And apologize, it's a bit small. For example, if you are using the yellow line on top, which is fossil LNG with a diesel dual fuel engine, you will still be acceptable to be used as fuel until 2035. And thereafter, there will be, you see the gap between 2035 to 2040. You'll only be compliant only if you're using HVO from waste. The green line denotes bio LNG from waste diesel dual fuel engine. So that will be compliant until 2015. So this is still, again, under proposal, but it just goes to show how regulations are in place to ensure that the use of alternative fuels will take up within this next couple of years. So next I'll go into seeing what we see from the alternative fuels and status and activities in the market. So what I have plotted here is actually 3 graphs of the new building orders from the 3 years from 2020 on the left, 2021 in the middle, and 2022 on the right. On top, these are vessel numbers, and the graphs or the pie charts below are the denotes the vessel cross tons. So we separated LNG carriers to avoid confusion here with other vessels fueled by LNG. So what we can see, obviously, is that there is a strong increase or interest in LNG, and an increasing share of LNG and methanol shares gross tons because of the very large container orders as we have heard from the previous speaker. So as an interesting observation here is that even in 2022, there's a small number of vessels that are being ordered, but the increase in gross ton is very much larger, as the large vessels will be needed for fuel to operate. But these accompanying slides just illustrate further my point that LNG fuel ships are really covering a large area. You can see specifically around the European regions. And within the, in green here, you see the LNG bunkering infrastructure that is being developed to supply the growing fleet. There's currently 775 confirmed LNG fuel ships and additional about 221 LNG ready ships based from these illustrations here. And most of them belong to the categories of the container ships in the largest bar chart, followed by the car carriers, as well as the tankers. So in considering the other fuel options, definitely cost is a key here. But what this illustration represents is all the different factors which make up what will be the determinant alternative fuel choice. So availability, for instance, on the left column there, it will be already available for MGO and LNG and LPG. For methanol, still a bit yellow, it's a bit unclear. For bio or e-fuels, hydrogen and ammonia, there's still lack of availability there. And self-explanatory for the different factors. Where we see the changes that may occur within this table here would be in the first and perhaps the second column. So this may change in 2035. This basically just represents one of our different scenarios that DNV has forecasted. So that's what our first speaker initially presented in terms of projections of the different fuels. We see definitely with the increased interest with bio and e-fuels, hydrogen and ammonia, availability in that front may change. And with regards to the detailed studies with the infrastructure and storage, colors on that front for ammonia at least may change. So I'm also one of the, I'm the project manager actually for the ammonia bunkering safety study that we have been recently awarded with in conjunction with GCMD. So there's a lot of interest and uptake with regards to the safeties of ammonia that has to be uncovered first before ammonia is a safe fuel to be used within the maritime. So this is just again an illustration of how the possible picture in 2035 may look like. Storage challenges, as we have heard as well from the previous speaker, would change with the different take-up of alternative fuels. This is just an indication of an ammonia version of a 4 by 1,750 meter cube tank on board from Delta Marine. With hydrogen, as you can see, with the expected similar operational profile, you would need to have 6 to 10 times an increase in the bunkering intervals. And then or the fuel tank volume for ammonia is about 4 times. So these are the considerations when it comes to the ship owners having to decide what will be the repercussions with the new ship designs with the alternative fuels. I mentioned this a little bit earlier on the work that we are doing with GCMD on the ammonia bunkering safety study. We see commercial take-up of ammonia only happening perhaps in mid-2030s, with the availability of the engines from the engine makers coming in mid-2025 onwards. So this will start with the 2-stroke engines and then subsequently be extended to the 4 strokes. So there have been a couple of studies that we have performed similarly in the port of Rotterdam as well as Oslo. And yeah, happy to share that perhaps during the panel session. Beyond alternative fuels, what are the other considerations that we can that are available in the options here? So I think we had a little bit of this in the first speaker, reducing energy consumption via optimization of logistics and digitalization, the increased use of enhancements in the hydrodynamics, or even the machinery, when it comes to the machineries within the vessel itself. We spoke a little bit, well, a lot, basically on the center portion there on the low carbon energy. And now it's the CCUS portion, which again has also been covered perhaps by our counterpart in IMarEST. So when it comes to maritime CCS systems, there are basically 3 points to be considered here. The system itself, whether it's a post-combustion or the pre-combustion, as mentioned earlier, has to be taken into account. Whether how the clean gases leaves the air, okay, and how CO2 is then captured as an agent, yeah, or as a pure stream. The treatment systems, the regulatory perspective is still unclear. And when it comes to storage, whether it can be stored either as a solid or a gas or a liquefied form, typically as a CO2 transport, within the CO2 transport conditions. But basically CCS is easier to apply on an LNG and an LPG fuel system, as we can see. So finally, we reached to the point on how DNV typically supports the owners, banks, and insurance. We have a fuel selector service or solution that we typically share with the ecosystem here. So this encompasses 5 main points. We basically, again, looking at what is the trajectory of emissions that the ship owner would like to set when it comes to having its goal target setting. We look at the review of the feasibility fuel strategies, as well as the economic potential of the fuel strategies. And so this is typically an iteration loop between what we consider a techno, economic, or commercial study. Finally, then we look into how this impacts the strategy and the fuel design and future operations of the vessel, and look into a specification review or detailed study in terms of how this feasibility analysis can then be applied to the detailed design of the vessel itself. This is just an illustration of our fuel path model, looking into the operational profile of the ships, the trajectories, as I've mentioned, as well as the design options, put it into the fuel path model, which includes the pending fuel prices, as well as the estimated total cost of ownerships that's being turned out as the outcome of the model. We have also been very active in the signatories within the Poseidon Principles. As I mentioned, there's been an increase in the take-up from the different banks and financial organizations here. And we have published a few, well, more than a few, I guess, in terms of the references and publications that we typically share on a yearly basis in terms of all the different, that encompasses all the different services and solutions that DNV has. So the key takeaways here are these 3 points here. There will be a more diversified fuel mix. LNG is definitely of strong interest. We are still experimenting in the other alternative fuels. Fuel and technology costs are the deciding factors. But beyond that, you could recall that 6 main factors I've shown previously: structure, safety, some of them, which will be a function of basically fuel and technology costs. And when facing uncertainty, choose the right partner in terms of deciding how to navigate these different choices that you may have with alternative fuels. So that's all I have. Thank you very much.
Yeah. Thank you very much, Dr. Imran Ibrahim, for your delivering the speech, Alternative Ship Fuels, Status and Outlook. So now I would like to invite our moderator, Mr. Shane Balani, from Decarbonisation Consultant, Lloyd Register, for the panel discussion.
Thank you very much, and thank you to the speakers for an insightful session. We heard our speakers talk about the numerous challenges that we're all aware of: technical, economic, regulatory, environmental. And it seems like a very complex outlook for the ship owners and those who need to invest in these options going forward. I'll try and group together some of the questions for each person, and then maybe we can have a bit of a question for everyone together and a bit of discussion. But if we start, there are many coming in clearly, with our partnership with classification societies. Could you comment on what you think some of the key tipping factors are behind the choices that need to be made by the ship owners, those who are investing in those ships?
Yeah, sure. Thanks very much for the question. So that's really very pertinent at this point. So what we have been seeing, at least in my role in the last 1.5 years, when we look into supporting new projects, close to 60 to 70% of all the inquiries coming in are all going in for use of application of alternate fuels, and most predominantly for LNG as fuel. But more recently, like maybe within the past 6 months, we're seeing sort of tipping, then going towards other fuels, like for instance, methanol, sort of coming up. And I would think maybe some reasons for that is firstly, for instance, the increasingly changing regulatory landscape. So for instance, we are seeing that CO2 in itself will be regulated increasingly more stringent. So we could see the regulations like, for instance, CII coming up, and LNG being a fossil-based fuel, definitely, although much more cleaner, definitely has an emission factor associated with its use. And also, it also has the consideration from methane. So depending on the engine type that you use, you might also see unburned methane escaping from the ocean. So which, when we look into the greenhouse gas emission study, the fourth one, we see from 2012 to 2018, the percentage rise was close to 87% in terms of the unburned methane emissions from vessels. So essentially this, like, along with the CO2 emissions, will increasingly be regulated. So that is actually giving ship owners sort of push towards, let's say, going into other cleaner forms of fuels, like for instance, methanol in this instance, and also ammonia. So that maybe are two factors that I see why it is sort of suddenly a shift, let's say, from LNG. Please.
Well, from my perspective, beyond price, because the owners are looking at the safety considerations of the different fuels. So in the study that we are managing, as I mentioned, we are involving a wide variety of the bunkering supply chain maritime profile. Beyond just the ship owners, we are looking into the fuel producer, for ammonia, in this case, it's Yara. We are involving terminal operators as well, the stakeholder who would be operating the fuel from quayside, and regulators as well. So industries, when it comes to bunkering, and with it being used as fuel, other considerations have to be taken into account. I think the key considerations for bunkering study, I would say, is determining perhaps a realistic number conceptually first. And that number has to be hinged upon what will be the demand for ammonia and CBC coming throughout. And from that number, the throughputs, the parcel transfers, how often will this bunkering will take place? And then the resultant safety considerations to contour the toxic gas that will be determining from those numbers. So at least from that study, creating a narrative of this picture and presenting it to regulators is key. We do not want it to be too conservative, not too liberal, of course, in terms of how you see ammonia being taken up. So yeah, all this basically goes back to safety. So again, in my perspective, beyond price, because safety of the handling of these different fuels.
Thank you. And Dr. Imran, maybe we can stay with you for a moment, because you were talking in that answer, but also earlier about the other drivers which are coming into the industry, not just the IMO, the EU, for example, pushing harder, banks are forcing changes, cargo owners are also requiring more stringent rules. So with this new information being fed into regulators such as the ammonia bunkering safety study, how do you see potentially regulations at the IMO level changing? And how do we plan for that now? For example, if we choose to invest in LNG, but then perhaps we may be unsure about what the LCA implications are later.
I think you've put it quite nicely in terms of what are the basic challenges from the ship owner's perspective here. I think the short answer I would say would be to be participating in GIPs. So the owners would have to keep a wide eye in terms of what are the latest trends with regards to the take-up rate perhaps of ammonia. Another factor I would think as well is, and I'm perhaps plagiarizing some of the lines that I've read within the articles, involving both in academia or institutions. So having the creativity coming in from academia, as well as merging that creativity with industrial realism, which is happening within the industry. So the business considerations, the commercial costs with regards to understanding not just an implementation of technology coming from academy, as well as we are looking into basically the bread and butter. How much will it cost having all these different fuels being implemented? So it's an iterative cycle, I would say, and yeah, the best option I would say for the owners would be to bear in mind all these different considerations and participating in the conversations here.
Staying on a similar theme, then, Sobhith, on the uptake of methanol, you may have seen the methane pledge coming out of COP26 last year about reducing methane emissions. How do you see regulations such as this affecting the uptake of perhaps the slightly more mature technology like methanol that's available today?
Yeah, so that is a very important part. So that's why I mentioned in one of my first answers, ship owners increasingly concerned about this methane slip and how it's going to be regulated. So when we look into this global methane pledge, so it's coming, that pressure is not just coming now from regional bodies such as EU, it's coming in from a much global perspective. So IMO will definitely have to take some steps to then address this particular challenge from methane slip. So when we look at methane slip, then we are specifically focusing on LNG, even if it's coming from fossil-based sources or even renewable sources or even bio sources. There is always this challenge of addressing this methane slip. So if we let's say look into specifically as to what's in picture now, let's say from the EU. So if we look into the EU fuel EU maritime requirements, then we are seeing that they are assigning specific values or emission methane slip values against the specific fuel and engine technologies that you use. So if let's say you are using LNG as fuel, and then you are installing an auto cycle based diesel engine on board, then you have a higher factor as compared to what you would have for, let's say, a diesel cycle LNG fuel engine. And if you look the same across for methanol, then that particular factor is zero. So that essentially is definitely providing a much more sort of an incentive for ship owners to consider technologies like, for instance, methanol to consider from this particular regulatory development. Thank you.
Thanks, Rick. On those factors that you mentioned, perhaps I can go to Mr. Wandy for a moment. Could you comment a bit on the well-to-weight concept that you mentioned, and this life cycle assessment in the context of different carbon capture technologies, as well as possibly LNG and other fuels which could be used, and how effective do you think they all can be when we're considering them on a full well-to-weight basis?
Okay, so well-to-weight means when we talk about the GEOC emission, it's not sufficient when we talk just about the emission from burning the fuels. We also need to know how the fuel is produced, and it may also produce additional GHG emissions. So that's why there is such term called like gray fuel or orange fuel, blue fuel, or even green fuels. So just like in my presentation, I mentioned that, for example, for ammonia, if you consider gray fuel or gray ammonia, the emission might not be saving, or it could be even worse than even HFO. But when you consider to produce ammonia in a green way, the GHG reduction is huge, can be up to 75%. But of course, in the end, when we talk about, yes, it's great, we want to go for green fuels, but the TRL level is not yet ready. That's why I think a lot of people are emphasizing that we are going transitions. So the best option is there, but it needs time to develop that. So we are going like, of course, we in the maritime industry, we just not just stay and just wait until the technology is ready. We need to do something about it. Before we do transitions, we explore other technology. For example, let's start with LNG. Maybe we can convert them to go to bio LNG, and eventually once ammonia or hydrogen is ready, then we can do. But we don't know when. The development is there. There are some promising projects out there showing that they are maybe start going for pilot plan or trial. But in the end, like what we want is actually whether it's ready for commercialization. So when we decide about which alternative fuels, I think I emphasize again that it's a transitions. We try to do our best what we can do now at the moment, which we also need to consider from the ship owner perspective. It need to be economically make sense. Yes, all of us, we want to go for ships decarbonizations, but we also need to consider all parties, and slowly actually we go transitions for maybe, for example, like low carbon fuels, and eventually we opt for the no carbon fuels.
Thanks, Ben. Wandy, let's stay with you for a moment. There's another question. You mentioned CCUS, so carbon capture and utilization, where we've actually used that carbon possibly in shipping, possibly in other industries. How can we be sure in shipping and the regulators for shipping of what happens to that carbon once it's captured? And are we using it in a place which is just going to be a time buffer before it's still emitted into the atmosphere? And how can we as shipping be sure when we invest in this technology, it will withstand those kind of regulatory challenges?
So when we talk about CCUS, actually it consists of two parts. First, the capture itself. The first question is how we capture the CO2 in a sustainable way. The second portion is the utilizer. Of course, there are talks on how whether we can utilize the CO2 on board, but at the moment, since the development is still on the CO2 utilized on land, we all know actually regulation for CO2 for land is much stricter than maritime. So, of course, at the moment, ship owner or like shipping industry try to capture, let's say you opt for this carbon capture, you store the CO2, you need to transport it to land, and someone needs to use it. And these parties, the one who plan to receive or do utilization, they need to meet the at least the port or local regulations, which of course this one need the support from the land-based authorities, but it thinks that of course the regulators between the shipping area and the ports area need to work together. But I believe that the regulation in the local need to be in place before someone there to actually receive those CO2 and they process it.
One question for Dr. Imran, but perhaps we'll actually ask everyone. What's the role of offsets and market-based measures in reaching net zero situation? And will the emissions mitigated in a maritime ETS, an emission trading scheme, be monetized in other industries? And can you see that happening? So, Dr. Imran.
Yeah, to create a level playing field for the cost of current fuels versus alternative fuels, market measures have to be implemented. To which degree of those different market measures will be determined by, I would say, different regions. So there's no question, I guess, in terms of relying carbon offset pricing. Ensure that when we are using, we are trying to change the status quo here. Yeah. So we have to, it's a bit of a carrot and stick, perhaps. Yeah. So the market measures here is the stick approach. Yeah. So that's my response to that.
I think totally agree with what Dr. Imran just mentioned. So when we did some analysis in terms of the total cost of operation, especially for ammonia fuel ships and also methanol fuel ships. So even when we are using what's currently available in terms of the gray ammonia or gray methanol, it's not really financially sustainable to operate vessels with these fuels. So when we look into, let's say, green or let's say the renewable or biofrost sources for ammonia or methanol, then the prices are the prices at which these studies are done or projected will require carbon pricing in terms of sort of at least $300 to $400 per ton of CO2. So essentially, to sustain the operation of these vessels at this particular sort of TCO, carbon market measures definitely would be needed. And of course, if those taxes or whatever it's collected during that particular set of regulatory development, if that's actually used ashore to develop infrastructure that's required, let's say, for this production of these facilities or these green fuels, then that would be money well spent. So that would be obvious.
So yeah, I think most of us have similar opinions. In the end, that carbon tax is also one of the driving force. Why it's been implemented in the first place is because without this, then no one will try to move and make changes. So yeah, I think for the rest, I have the same opinion.
I guess that's a good thing. Strong alignment amongst the panel. A couple more fuel-specific questions. So, Sobhith, you mentioned biomethanol may be one route to start achieving methanol usage in the shorter term. How can we be sure about the impact on fuel, food production, and other sources of bio carbon, let's say, from bio source, being managed effectively?
Yeah, so that's a challenge we always discuss. And then I still recall back in 2006-07, when there was increasing demand for biodiesel, then that really had an impact on the food prices that we had. So this was not really gone unnoticed by the regulators. So if we look into EU, how things are being structured now, they are looking at production of bio-based fuels, and they are putting standards to make sure that these are coming from, let's say, sources other than direct food produce. So for instance, bio waste, municipal waste, or even waste from food processing or other industries, agricultural waste. So with that in mind, although bio-based sources will play an increasingly big role in the green fuels, we could see with the regulators playing a bigger, more important role now on understanding the situation, it might have, let's say, a lesser impact, at least in terms of the food prices as we see now.
Just wanted to add on as well. I think we've been speaking about decarbonization, but I just want to put maybe digitalization in the agenda as well, because it's to respond to the questions I guess you asked here. I think the issue here is to make sure that the green credentials of the fuels are certain. So in that sense, there is a digital passport service that DNV has developed to ensure within the whole value chain, the supply chain of the these green fuels are true. So I do not have the details, but with regards to, it basically entails ensuring that the nodes within those supply chains are good enough, are validated, certified, and it encompasses all the different factors, I guess you mentioned earlier. So there are existing solutions to this, but it's again it's a function of perhaps the take up of the ecosystem to ensure that that these solutions are viable.
Dr. Imran, there's one more question for you, so I'll hand this back in a moment. Or for any other comments on the panel, this is probably a prelude to a later session on nuclear-powered shipping. But obviously, nuclear ships have been in service for decades now already, and the Navy vessels and certain icebreakers and so on. What do you believe is hindering its uptake in the growing pressure of decarbonisation?
Yeah, we are aware of the various solutions with regards to nuclear as well. Most pertinent perhaps is the molten salt reactors that are available currently. But the question remains with regards to, again, regulations of these nuclear reactors, the perception basically from industry, whether it's really safe enough, and whether it makes both technological and economical viability when it comes to owning assets with regards to nuclear vessels. So it's somewhat perhaps similar to the challenges with the different alternative fuels. And yeah, it's a function again of how the take-up of industry would be able to accept perhaps nuclear as a fuel for commercial shipping.
Yes, Dr. Imran mentioned the perspective. It's about the perception. But maybe just I would like to add what we have been doing in LR. So there was also again this same interest, let's say back in the 70s when the oil price was really going up. And at that point, of course, we had developed our own set of rules and all those for supporting projects that were coming on board. And even back in 2010, there was further again interest in terms of nuclear fuel projects. And what we had developed back then was also used to support some of the initial design developments of these projects. And even currently now, of course, this would form a mix, form an important component within the mix. So there's definitely opportunities for us to work closer with developers and also interested owners in this particular sector.
Thanks. Wandy, one more question specifically on CCU, and you mentioned the physical footprint of the different systems can be quite different. Can you elaborate a bit more on what that could be like, and is it applicable to certain ship types more than others? And one other question I'll add on to that is it actually worth the amount of additional energy we put into these carbon capture systems on board ships versus using that energy, perhaps if it's green energy in particular, in some other land-based application or on reforestation or something like that instead?
Okay, so yeah, I think this is a really good question. So I think in terms of the applicability, yes, there is a certain limit of you need to maintain certain spaces. Right? So generally, I think for small scale ships such as, for example, hovercraft, all these, it might not make sense to install CCUS because they have a limited size. It's more makes sense for them maybe to just switch to another fuel or just using a drop-in fuel to meet the requirements. So for the size wise, I think CCS most likely applicable for the ocean going vessel. Size wise, in the end, is really on the economic basis and also depend on the ship types. I mean, when we talk about dry bulk, container, or cargo, you also need to consider they do have space, but it means they lost their quality. It means about the economic sense. So at the moment, I cannot say that it's definitely applicable for certain sets, but what I can say is there is certain sets that need to be maintained, and it's unlikely for the small type of ships such as hovercraft to install this kind of system. And then, I'm sorry, what is your second question?
The second part was on the energy usage. So there's more energy required to power the CCU system on board? Is it actually worth the amount for the savings that we get, or should we be using that energy at other places?
Yes. So in the case study that I showed in the presentation, right, why the cost of the CCS is high is because if you want to convert to higher CO2 capture up to 90%, existing energy is not sufficient. So you need to consider installing even additional generator to produce them. Like you say, you need to use more fuels. So of course, this is part of the issue that need to be addressed in development of CCS. So I think some of the development are also focusing on how to recover the waste, replace it, because the main energy consumption for the CCS is actually for the regeneration process. It means that you need to reheat it again and actually lower the temperature during the absorption. Right? So one consideration is why not try don't use additional fuel, but instead try to recover the waste heat. For example, after the turbocharger, you have certain amount of energy that you might be able to recover. But of course, like you say, if in the end it's not possible, then it will come to the economy again. If it doesn't make sense, like you said, the energy is really high, why not use the others? Then it's probably CCS is not applicable for this application.
Okay. So good timing. With our last 2 or 3 minutes, I'll ask one last question to the whole panel before we hold everyone up for lunch too much more. Reflecting on the first session and what was mentioned about the IPCC report, perhaps 30% of Singapore is going to be underwater at some point. So what are the next most practical steps that ship owners can take, considering all these different factors we talked about, technological readiness, economic challenges, regulatory uncertainty, and so on? It's a difficult question. Perhaps Dr. Imran, I'll ask you first and then we'll go around.
Yeah, I guess the last question, right? I think we've spoken a lot on what will be the future fuel or the forecasts perhaps of how alternative fuels will be taken up. And I'm plagiarizing here again in terms of the line here. But the true future fuel perhaps that we see will be collaboration. To ensure that there will be transparency between information that's being shared again from academia and industries, so that the ship owner will be making an informed decision.
Yeah, so maybe one of the aspects that that ship owners might also would like to take into account is if, let's say, they are making their bet on one particular fuel now, they are doing that with, let's say, some form of flexibility to adopt to another, perhaps in the near term or in at least in mid to long term basis. So that's one thing that we increasingly see a number of ship owners are also doing. So I expect that to continue for the near term new shipbuild orders.
So I think the situation is very dynamic, as I mentioned before. It's very depend on what is the situation for individual ship owners. For example, if your ships already finished their lifetime and you're planning to develop new ships, then your option will be very different compared to the existing ships that already maybe still have another 10 or 15 years down the road, which maybe it doesn't make sense for them to recall everything. Then they maybe even consider they might have more limited options. So I think, as I mentioned, it's really dynamic. We will observe and depend on every projection, right? In the end, we have to see which fields that can develop fast, then which field that can have a ready in terms of supply and infrastructure.
Sounds like quite perfect timing. So thank you very much to all the panelists once again. I'm sure we'll be around lunchtime if anyone has any other questions we didn't get through. Yeah, thank you very much.